Okay, so now let's talk about the material in section 6.3, diagonalizable. So last time we talked about section 6.1 and we say in linear algebra, if I give you a matrix, in linear algebra, matrix is an important concept. Matrix, if we have linear transformation, then we could consider its matrix representation, and so we could view a linear transformation as a matrix. And for a matrix, the most important thing about a matrix is to find its eigenvalue. Actually, to find its eigenvalue. Yeah, just in some application, you will see that an eigenvalue of a matrix is an important concept. It's an important concept. So if I give you a matrix, and then in section 6.1, we know that we should figure out its eigenvalue. Just consider determine A sub lambda I equals 0. Just figure out its root. Yeah, and now, but if the now, if the matrix is of the form, for example, A is 1, 3, 0, 0, -2. Then it's easy to see its eigenvalue is that because it's upper triangle or diagonal entry, so it's easy to see 3 and -2. They are eigenvalues of A. 3 and -2, they are eigenvalues. Of A. Right? 3 and -2. And how about its power? I mean, for example, A squared. For this kind of matrix, it has some useful result. It's very nice matrix. Diagonal matrix is very nice matrix. For example, if you consider A squared, what's this? It's exactly, if you compute it directly, 3, 0, -2, you will see just in diagonal entry you should square it. So you could get this one, right? So what's the eigenvalue of A squared? A squared is the matrix A squared is this one. So of course its eigenvalue is 3 squared. -2 squared is the eigenvalue. Of A squared, right? Of A squared. And so on. I mean, if you consider A to the power of n, then what's the matrix A to the power of n? Actually, follow a similar way, you will see it's of the form. Then what can you say about its eigenvalue? It's exactly 3 to the power of n, -2 to the power of n. It's the eigenvalues of A to the power of n, right? So if it's diagonal matrix, it's very nice matrix. It has some nice property. For example, its power is of the form. So for its eigenvalue, it's easy to compute. And even of course, and actually you could consider another one. I mean, for the matrix A, probably in some topic you will see the form. For example, sine of A. Of course, you should define this matrix or exponential A, and so on. Yeah, and you will see if it's diagonal matrix, it's very nice. It's very nice to see its eigenvalue. But for this part, now in this step, we could skip it. Just tell you it's very nice if it's diagonal. Okay, so but for the general matrix, probably it's not diagonal matrix. So of course it's not diagonal matrix. Probably most of the 2x2 matrices are not diagonal matrix. Then do we have some nice result? For example, like this one. Do we have some nice result? So now we talk about diagonalizable. What does it mean? So of course we should tell you the definition. Diagonal, and give you the example. For example, here A is n by n matrix. It's not. If we call A is n by n matrix, and if we say A is diagonalizable, what does it mean? It means that of course, for the matrix A, probably it's not diagonal originally, but as we say in section 6.1, but we could find, but it's equal to some A equals PDP inverse. This one, PDP for some diagonal matrix D, for some diagonal matrix D. Then it still have some similar nice result. This one, some similar nice result. And what does it mean? Remember that if we say A equals PDP inverse, and here D is diagonal. I mean probably A is not diagonal, but probably, but it's equal to P times some diagonal times P inverse. And it also means that A is similar to D. A is similar. For this one, it means that similar. A is similar to diagonal matrix D. It means that A is similar to some diagonal matrix D. Okay, originally A is not diagonal matrix, but if A is diagonalizable, it means that A is similar to some diagonal matrix D. Then for this diagonal matrix D, it has a nice result. And for the matrix A, it also has some nice result. That's what we want to show. Okay? So do we have some example? Yes. Our previous example in section 6.1, we have talked about this one. A equals 6, 3, 2, 3, negative 2. For this example, I will show you. And in this section, the most important thing, actually I will tell you. Of course, we know that how to, in section 6.1, we know that how to figure out its eigenvalue, how to figure out its eigenspace. But in this section, we want to know what's the immutable P. Could you figure out the immutable P? And what does the immutable P means? And another way is, now I will really give you the A to the power of n, some power, and then I want you to figure out its eigenvalue. For example, A to the power of 10. What's the eigenvalue of A? What's the eigenvalue of A to the power of 10? What's the eigenvalue of A to the power of 10? Something like that. Okay. So, and then we want to find the immutable matrix P. Yeah. Okay, so let's see how to see that it's diagonalizable. Actually, for this matrix A, it's diagonalizable, but how to see that? Yeah. And first of all, of course, you should figure out its eigenvalue. But in order to find its eigenvalue, just the example in section 6.1. So we could try it soon. Yeah, we could try it quickly. Determine A subtrate lambda I, so it's 3 subtrate lambda. It means that for its diagonal entry, we should subtrate lambda. So 3 subtrate lambda, negative 2 subtrate lambda, and for all of them, just keep it, and then it's equal to 3 subtrate lambda, negative 2 subtrate lambda, subtrate 2 times 3, 6. So it's equal to, let me see, A subtrate lambda, yeah. A subtrate lambda, yeah. So it's equal to negative 6 subtract, let me see, plus 2 lambda, subtract 3 lambda, plus 2 lambda, plus lambda square subtract 6. So it's lambda square subtract lambda, subtract 12 equals 0. So it's equal to lambda, it's lambda 3, 4, negative positive. So lambda plus 3, lambda plus subtract 4. Yeah, it's our previous example in class. So indeed, you could get this one. It's equal to. So finally, what's the eigenvalue what's the eigenvalue? Eigenvalue is negative 3 and 4. Eigenvalue is negative 3 and 4. If you remember that, eigenvalue is negative 3 and 4. Just for, it's the same example, so I just introduce it quickly. Yeah, but you could check it again. And for the eigenspace, so for this part because now I want to tell you what's the matrix P and how to know that they are diagonalizable. I mean, how to know that this equation, indeed this equation holds. And later I will tell you if we have this equation, if we have this equation, indeed we have some nice result. Yeah, later I will tell you. If we have this result, it will be better to understand some question. Okay, so we have two eigenvalues. So here we could denote by lambda 1. We could denote by lambda 1 and lambda 2. So lambda 1 is negative 3. So first of all, it's eigenspace. So null space of A subtract lambda I. So it's negative 3i. So it's exactly null space of A plus 3i. A plus 3i, so it becomes null space of the matrix plus 3. So in its diagonal plus 3. So it's 6, 2, 3, and plus 3. So it's 1. So this matrix is null space. This matrix is null space. So it's our 6, 2, 3, 1, 0, 0. So usually to cancel this one, so negative 2, then you will get 3, 1, 0, 0, 0, 0, this one. And we label it by S1, S2, right? And again, here, it means that 3S1 plus S2 equals 0. It's stated by this equation. And so we could let S2 be negative 3S1, negative, right? Let S2 be negative 3S1. So its null space is the solution set of this matrix, and it's this solution set. So it's our S1 TB S2 equals negative 3S1. So S1 is any real number here. Okay? Yeah, just this part we just probably is something, it seems that we just review it. Yeah. And I will start from this part. And lambda 2 is 4. It's equal to 4. And the null space of A subtract 4i is exactly null space of A subtract 4i, so it's subtract 4. 3 subtract 4 is negative 1. Negative 2 subtract 4. Subtract 4 is negative 6. Negative 6. And 2, 3. TB. 2, 3. 2, 3. This one. And what's this? Here, now it becomes negative 1, 2, 3, negative 6, 0, 0. And so use this one to cancel this one. Then what will you get? Negative 1, 2, 0, 0, 0, 0, 0, 0, 0. And now denoted by S1, S2. So what does it mean? It means that negative S1 plus S2 plus 2S2 equals 0. Negative S1 plus 2S2 equals 0. So S1 equals 2S2. So S1, move it to right, S1 equals 2S2. So it's exactly S1 equals 2S2. 2S2, S2 could be any real number. S2 could be any real number. This one. Okay, so so for this part, you should pay more attention here. Yeah, we want to have the form. And here I erase it. Yeah, I erase it. Okay, so for this part, you could view it this way. Here, as we said, here is exactly means the span of this vector. Just tell the it's equal to S1 has 1 negative 3. So we could write it this way. It's 1 negative 3. It's space at 1 negative 3. And for this one, you could view it this way. It's S2 times 2, 1. So it's exactly space set of 2, 1. 2, 1 vector. Space set of 2, 1 vector. Okay, and our goal is to find to show that A equals PDP inverse. Our goal is to find this one. Our goal is this one. And for this one, for this equation, in both sides, if you multiply by P in left hand side, if you multiply by P here, what will you get? You will get AP equals PD times P inverse P. This one. But P inverse times P is equal to identity. And the PD times identity is exactly equal to itself, PD. Okay, in other words, if this equation holds, A equals PDP inverse, then what can we say? Then it's equivalent to this one. AP equals PD. Okay, AP equals PD. So here is a tree, and it's very useful. I mean, how to find the matrix P? Actually, we consider its eigenvector. We consider the eigenvector, and you could choose this one, and choose this one. Okay, and let me show you. If I let lambda 1 be -3, then we denote it by our V1. And the lambda 2 be 4, then we denote it by our V2. Okay, so now we let V1 be this vector, 1, -3. And the V2 be this vector, 2, 1. Then what do we have? We know that this vector V1 it belongs to its null space, A plus 3i, right? So what does it mean? It means that A plus 3i equals V1. Not equals V1. A plus 3i times V1 is equal to 0, right? And it means that AV1 equals -3V1. Actually, for this one, that's why what we say V1, if we choose this one, V1 is exactly eigenvector. It's exactly eigenvector of A corresponding to eigenvalue number -3. And V1 is exactly, if we satisfy this equation, it means that V1 is an eigenvector of A corresponding to eigenvalue -3, right? And V2, we have this one, A subtract 4i. V2 belongs to its spanning set. So V2 belongs to this one, it's null space. So in other words, this equation holds. And then it also means AV2 just separate it and move it to right hand side. AV2 equals 4V2. And it exactly means that A4, sorry, V2 is exactly the eigenvector of A corresponding to eigenvalue 4. V2 is exactly its eigenvector. Now, what do we have? We have the matrix A. Our goal is to show this one. So what's the matrix P? Here you could see that we have a matrix A, and A is this 2 by 2 matrix. A is the matrix 3, 2, 3, -2. A is exactly this matrix. And what's the matrix P? For the matrix P, just in first column, we consider V1. In second column, we consider V2. Then what do we have? When you consider this one, you will see here in our example is 1, -3, and in our example is 2, 1. In our example. Then what do we have? It's exactly in the first column it's AV1. Second column is AV2. This one. Actually it means this one. It's 3, 2, 3, -2 times 1, -3. 3, 2, 3, -2 times 2, 1. AV1 means their product. AV2 means their product. And what's this? AV1 is actually -3V1. So it's -3V1. AV2 is 4V2. 4V2 is this one. Right? And it means that it's -3 times V1. So it's 2 by 2, 2 by 1, so it becomes 2 2 by 2, 2 by 1, 2 by 1, yeah, 2 by 1. So for this 2 by 1 is negative, every1 equals negative 3v1, so it's negative 3 times v1 is 1 negative 3. And then here is 4 times v2, 4 times v2 is 2, 1, this one, this one. So for this matrix, it's a trick. It's a trick. Here, it's equal to this one. But what's the matrix? What's the matrix? You could write in this way. It's very important part. It's very important part. You could view it this way. It's the we could put v1, v2, and multiply by negative 3, 4. Just put down the coefficient negative 3 or the eigenvalue. The first eigenvalue in the first diagonal entry. And for the eigenvalue 4, put it down in the second diagonal entry. When you consider the product, what's the product? Indeed, this first row times first column, so negative 3 times this guy. Second row times first column, so it's negative 3 times this guy. So indeed, first column is still negative 3v1, right? Negative 3v1. I mean, here 1, 2, 3, 4 times negative 3, 0. Okay, here you could see that our v1, here our v1 is 1, negative 3, 2, 1. Here, when you can see negative 3, 0, 0, 4. What's this? What's this? It's equal to negative 3 times 1 plus first row this kind. So it's 0. So just have this term plus 0. And here negative 3 times negative 3 plus 0 in first column. And the second column is 1 times 0 plus 2 times 4. And then negative 3 times 0 plus 1 times 4. This one. This one. So for this part, for the first row, sorry, for the first column is exactly negative 3 times 1 negative 3. It's exactly this one. It's exactly this one. This term negative 3v1. And then this one, the first term they are 0. So actually, you could view it, it's 4 times 2, 1. So it's exactly 4 times 2, 1, this vector. This vector. So it's a steer. It's important. It's very important because it has the form. It has the form. Of course, you could memorize this result directly, but I tell you the process, and later I will tell you I tell you the detail. Yeah, but later I will tell you the process to solve it. Okay. Yeah. Okay. So you have the form. So now, once we have this form, here, what's this? Here v1 is 1 negative 3. v2 is 2, 1. So you could check it. It's equal to this one. So what's our matrix? So now we just need to let P be. We just need, our goal is to find the matrix P such that AP equals PD. Remember that? Here AP equals PD. So now we have a matrix A here. And then we have a diagonal here. Just in diagonal entry, put the eigenvalue lambda 1, put the eigenvalue lambda 2. So we have, indeed, we have diagonal matrix P. And then here we have the matrix which contains v1, v2 in first column and second column. And then the same matrix P over here. So if we let P be this guy, v1, v2, and it's exactly 1 negative 3, 2, 1. And then what's the matrix? Diagonal matrix D. Just the eigenvalue negative 3 and the eigenvalue 4. This one. Lambda 1, lambda 2. And then it's exactly 3, 0, 0, negative 3, 0, 0, 4. This one. Then what do we have? Then you could see that this matrix P, it's easy to see. If you can see its determinant, it's 1 subtract negative 3 times 2, negative 6. So it's 1 plus 6, so it's 7. It's non-zero. It's non-zero, so it's easy to see it's invertible. Since its determinant is non-zero, so it's invertible. is invertible. It's easy to see. The matrix P is invertible. So what do we have? P is invertible. And AP equals AP equals PD. AP equals PD. AP equals PD. And the P, what's the matrix D? D is exactly 3004. Negative 3004, this one. And now we multiply by P merge in both sides. Then indeed A equals P negative 3004 P merge. Indeed we have this result. It means that A and B are similar. It means that A and B are similar. I mean, in all you can, yeah, and but here A is similar to this one, but it's diagonal matrix. So indeed A is diagonalizable. A is diagonalizable. A is diagonalizable. If a matrix is diagonalizable, it has some nice result. And indeed it's diagonalizable. But what's the invertible matrix P? It's exactly the eigenvector. So if you choose, so for the diagonal matrix D, first entry if you consider lambda 1, second diagonal entry if you consider lambda 2, then for the invertible matrix P, first column you should consider eigenvector V1, second column you should consider eigenvector V2. Okay? But if you change it, I mean for the diagonal matrix, if you consider 4, 0, I mean for the diagonal matrix, if you consider the diagonal matrix as this one, 4, 0, 0, negative 3, for just change negative 3 and 4. Then for the matrix, invertible matrix P, you should change them. You should change E. You should consider V2, V1. V2, V1. And it's equal, so it should be 2, 1, 1, negative 3. 2, 1, 1, negative 3. Okay, 2, 1, 1, 2, 1, 1, negative 3. Okay. And here, actually, this equation holds. So actually, for the invertible matrix P, it's not unique. It's not unique. I mean, actually, for this eigenvector, you could choose 1, negative 3. You also could choose 2, negative 6, right? So you also have the same result. I mean, since if the equation holds, in both sides we have the matrix P. So even you choose 2, negative 6, we still have this one. Since 2, negative 6 is still an eigenvector of lambda 1, is still an eigenvector of negative 3. Okay. Yeah, okay, so now, so the matrix A indeed is diagonalizable. So it has some nice results. Then here, let me tell you some result in this example, or general result. And tell you how to solve it for the process. And I will give you one more example. Then give you some notes. So if A is in this example you could see that A is 3, 2, 3, negative 2. Then A is, in this example you could see that A is diagonalizable. And for its null space, its dimension, null space of A, it has 2 eigenvalues. Negative 3 and 4 is the eigenvalue of A. So when you consider A subtract lambda, A subtract negative 3, so it's A plus 3i plus A subtract 4i. What's their dimension? Sum of their dimension. Remember that? Here, for the eigenvector V1, we choose the eigenvector from its eigenspace. But its eigenspace is a spanning set of this vector. So it's a null space is the spanning set of this vector V1, 1, negative 3. And the null space of A subtract 4i is the spanning set of 2, 1. of 2, 1. Of 2, 1. So both of them, their dimension is just 1 vector, so it's 1. So 1 plus 1, so it's equal to 2. And in this case, indeed, A is diagonalizable. Indeed, in this example, A is diagonalizable, and it has this property. Sum of their Null, for their Null space, their dimension, sum of their dimension of their Null space is equal to 2. Is equal to 2, and it's 2 by 2 matrix. 2 by 2 matrix. So it's diagonalizable. Actually, we have a general result. If A is n by n matrix, then what can we say if A is diagonalizable? Then our general result is this one. A is diagonalizable if and only if dimension Null space of A subtracted lambda 1I plus from here dimension Null space of A subtracted lambda Ki equals n. And here from lambda 1 to lambda K, there are eigenvalues of A. Counting multiplicity, they have K eigenvalues. And for each lambda K, we have some Null space. And for the Null space, it's a space of some vector. So it has the dimension. So once their sum of their dimension equals n, then this matrix A is diagonalizable. And this example. Okay. Okay, so now I give you the example, some example again. For example, A is 1, 1, 0, 1, and A is 1, 1, 0, 2. And one more example is actually in 1, 1, 0, 0, 2, 0, 0, 0, 2. It's the previous example in section, but it's it's Null space. It's fine, so okay, yeah, these two examples is enough. Okay, so how do we know they for these two matrices they are diagonalizable or not diagonalizable? How do we know? First of all, here, for example, here this matrix, if you check its eigenvalue, as we said, if it's upper triangular, then what can we say? Upper triangular, so eigenvalue of A. For the eigenvalues of A, we know that just 1. Its eigenvalue just 1. And for this one, its eigenvalue 1 and 2. 2 values, right? 2 values. So in this example, in first example, this case, in first case, if you consider there are several ways to explain it, but here we could follow this result. So its eigenvalue is 1. So now if you consider A subtracted 1i, A subtracted 1i, 1 times I is I. So it's A subtracted 1, so it's 1 subtracted 1, 1 subtracted 1, 1, 0. So it's 0, 0. So now it's 0, 1, 0. So it's 0, 1, 0, 0. It's Null space. So it's Null space. So you should consider this one. So it means S2 equals 0. S2 equals 0. So it's Null space. Why is it Null space? For the S1, we don't have any restriction. So S1 could be any real number. And S2 equals 0. This one. S1 is any real number. This one. S1 is any real number. So it's the spanning set of x1, 0. So its null space for this null space, its nullity is 1. So its nullity is 1. So its nullity equals 1. But it just have one eigenvalue. So its null space, its nullity, its nullity equals 1, but it's not equal to 2. So this equation doesn't hold. So A is not diagonalizable. This matrix is not diagonalizable. So denoted by B. So A is not diagonalizable. It means that we could not find, we could not find invertible B such that PAP merge, such that A equals P times some diagonal matrix D times P merge, this one. But actually, you also could do that this way. If we could do that, if we could find, we could not find. But you also could view it this way. If we could find a diagonal matrix D such that A is equal to PDP merge, then for the matrices A and D, as we say, they are similar because they satisfy this equation. So they are similar. So if they are similar, they have the same eigenvalue. But the matrix A is eigenvalue is 1. So D, this matrix, its eigenvalue should be 1. But D is diagonal matrix, so it should be 1, 0, 0, 1. Right? It should be 1, 0, 0, 1. So it means that it should be identity. If indeed we could find an invertible matrix P such that this equation holds, then the matrix D should be identity. So it's equal to P times identity times P inverse. But P times identity is P. P times P inverse is identity. So it's equal to 1, 0, 0, 1. But it's a contradiction. A is not equal to 1, 0, 0, 1. So it's a contradiction. So we could not find an invertible P. Okay, so it's also another way to explain it. But for this one, for the matrix P, you could see that it's then for this one, its eigenvalue is 1 and 2, and you could check it. B subtract I, 1I is equal to subtract 1. So it's 1 subtract 1, 2 subtract 1, 1, 0. So it's 0, 1, 0, 1. And the solution set, A0 is B subtract I0 is solution set. So it will be this way directly. So it's S2 equals 0. So indeed, its null space of B subtract I is exactly S1 could be any real number. S2 is 0, this one. And indeed, it has one free variable. Its dimension equals 1. And if you check B subtract 2I, you will have the same result, similar result. 1 subtract 2, 2 subtract 2, 0, 1. And it's equal to 0, 0, negative 1, 1. So you also could see that its dimension equals 1. Here we have two variables, right? And one is free variable, another one is D variable. So for its one free variable means that its dimension equals 1. So its dimension equals 1, so their sum equals 2. So we have this equation. So indeed, it is diagonalizable. Yeah, we could use this result. Okay. Yeah. Okay, now I give you the I give you the process to diagonalize a matrix A, and I will compute A to the power of n. Okay. Yeah. Okay. So probably you will better to. Okay. So we have this one. A P equals P times 3, 0, 0, 4. And as we say, why do we consider diagonalizable? One of the reasons is that now indeed we have this 10, and we want to know A to the power of 10. The question is A to the power of 10. or a to the power of n, their eigenvalue. We want to know. Okay, so now what can we say? We have this one, and as we say, a equals p negative 3,0,0,4 p mers. Now let's see what's a squared. What's a squared? A squared is the matrix A p negative 3,0,0,4 p mers. It's our A. Multiplied by p negative 3,0,0,4 p mers. Right? Then what can we say? Left hand side is p mers, right hand side is p. So what's their product? Their product equals identity. Identity. So and matrix times identity is equal to itself, and it times this guy. I mean, so it's equal to p times negative 3,0,0,4 times negative 3,0,0,4 p mers. Right? And now it becomes this one. So it becomes this matrix, this diagonal matrix is square. It's square, so it becomes p times diagonal matrix is square, negative 3 square, 0,0,4 is square, p mers. It has this form, So it's very nice, right? If A is over the form, then if it's over the form means that A is diagonalizable, then it's similar to a diagonal matrix. Then when we consider it square, you will see it's exactly equal to this one. Just in its diagonal, just in the middle of their product, in the middle matrix, it's diagonal, and we just need to square them. And it's diagonal matrix, so once we square them, it's very easy to compute. Just in diagonal entry, we square it. Yeah, and the left hand side will keep p, right hand side will keep p mers. The reason is that when we consider the product, we will cancel it. Just keep the left hand side, this part and this part. Right? And do the similar result. Could we write down a to the power of 10? Yes, just p times negative 3 is to the power of 10, and 4 to the power of 10, 0,0 p mers is our result. And once we have this result, what's the eigenvalue of this matrix? As we say, if it's of the form P and then another matrix D, if I call it D prime. So this matrix equals PD prime P mers, means that these two matrices they are similar. And if they are similar, means that they have the same eigenvalue. So a to the power of 10 is eigenvalue exactly these two diagonal entries. These two are diagonal entries. So it's very nice. It's very nice. Even A is not diagonal. Even the matrix A is not diagonal. The matrix A is this one. Even it's not diagonal, but if it's diagonalizable, it's also very nice. It has also very nice result. Okay. Yeah, okay, so now I write down the process and give you one last example. Okay. Okay, so it's the last example. Before that, let me tell you the note. The process to diagonalize. Compute a to the power of n, a to the power if a is inverse. The first step, we solve determinant a subtree lambda I equals 0, we get eigenspace, eigenvalue, and eigenspace. Of course, eigenvalue. First of all, we should figure out the eigenvalue. Of course, get eigenvalue. But for the eigenvalue, you should figure out the eigenspace. For any lambda I, eigenvalue from lambda 1, lambda 2, until lambda k. Counting multiplicity. And for any lambda I we solve, eigenspace is eigenspace. So it's eigenspace. A subject lambda I is null space. And if, as we say, if we satisfy this result, I mean, if summation, we have k eigenvalue, so I goes from 1 to k. If the sum of the dimension of the null space equals n, it's n by n matrix. Here A is n by n matrix. So if the sum of the dimension of the null space of A subject lambda I is equal to n, then A is diagonalizable. Then A is diagonalizable. So not all matrices are diagonalizable. Then in this case, how to find the invertible matrix P? Just find a basis for each basis. It means that we find an eigenvector. Actually, we find an eigenvector for each null space A subject lambda I, and then we combine them into the matrix P. So B1, B2 until Bn. Here, sum of the dimension of the null space equals n. It means that once we consider the basis of each one, then combine them, then you will have n vectors. You will have n eigenvectors. But for the eigenvector Vi, for some of them, probably they have some different corresponding eigenvalue. They have some different corresponding eigenvalue. Then what can we say? What's our result? Then our result is that you could just memorize this result directly. But for the detail, I will tell you. Then A equals P D P inverse. And what's the, so P is this matrix. And what's the matrix D? Here D is the diagonal matrix D1, D2, and DTK, Dn. Where AVJ equals DJVJ. AVJ equals DJVJ means that AVJ equals DJVJ means that Vj is the eigenvector of A corresponding to the eigenvalue Di. Dj D corresponding to the eigenvalue Dj. Okay. Yeah, here why I use another notation, not I is that probably it has some repeat eigenvalue, so we could rewrite it. So I just rewrite it. If I use the same notation, probably you will get confused because some of them it has some repeat roots, it has some repeat eigenvalue. So I use this notation. Yeah. Dj. Okay, so of course for the invertible P it's not unique. It's not unique. But as you see, it should satisfy this equation. So in other words, if you choose another invertible P, then for a diagonal matrix D, you will change. Because DJ depends on Vj. DJ depends on Vj. If you choose another Vj, probably the DJ eigenvalue DJ you will change. You should change. Okay. Okay, and then yeah, And for the process, for the reason I have already shown you. So let me write down the last step. And then why do we have this one? Remember that it's our AP equals PD. It's our AP equals PD. And for, as we say, it's just A V1 until Vn is equal to V1 until Vn times diagonal matrix D1 Dn. This one. It's over the form. For the reason. The reason is that it's over the form. Yeah, so I think it's the key point. But for it's the detail, so you could skip it. Yeah, just you should memorize this result. Anyway, so once you have A equals PD P inverse, we want to solve, compute A to the power of n, A to the power inverse. Then what can we say? A to the power inverse, A is inverse. It's equal to, it's PD P inverse is inverse. But its inverse, we have this one. AB inverse is equal to B inverse times A inverse. So this one is equal to P inverse is inverse times PD is inverse. And the first term, P inverse is itself P. The PD inverse again is D inverse times P inverse. This one. So what's the solution? If A is PD P inverse, what's the final solution? If A is PD inverse P inverse, for its inverse, it's just for the left hand side, right hand side, keep the matrix P and P inverse. Just in the diagonal matrix D, we can see that it's inverse. So in this case, now D is this guy. So what's the D inverse? D inverse is exactly D1, their reciprocal. Inverse, so just their reciprocal, right? If you multiply by its inverse, actually you could just consider its reciprocal for each diagonal entry. You could just consider this one. And when you consider their product, it's E to C is equal to identity. So this guy is exactly this matrix is inverse. So its inverse is 1 over D1, 1 over D2. I will give you the example. This one. And how about A to the power of n? Then it's similar. We know that A is square is PD, P inverse, PD, P inverse. So as we say in previous example, you will see you cancel it, become identity. So it becomes PD square P inverse. And finally, A to the power of n is exactly P times D to the power of n times P inverse is exactly this one. And again, D to the power of n is diagonal matrix, so it's very nice. It's D1 to the power of n, D2 to the power of n, until dk to dn, until dn to the power of n. Diagonal matrix. And we are done. Yeah, I mean it's the process. So of course I should give you the example. Then we are done. Then we finish this section. So of course I give you one more example. I have given you one example. Originally I have already given you an example. So now I give you one more example. Okay. Yeah. Okay. So let's see one more example. It's our process. Yeah. So for this one, yeah, probably will be okay. I can keep it. So now let's see the example. One more example. A is 1, 2, 2, 1. We want to find probably in section 6.1, 6.3. You should know how to solve this kind of question. Find its eigenvalue. Lambda 1, lambda 2 of A. And the second one, find its eigenspace. Find the eigenspace belonging to lambda 1, lambda 2. And then the third one, find a matrix P and the diagonal and an invertible matrix P and the diagonal matrix D, such that A equals PDP inverse, A equals PDP inverse. So as you see this form, it means that the matrix P is invertible. It's inverse, it's invertible, it's invertible. Once you see this form, it means P is invertible. And if it's a form, it also means you could multiply by P in both sides. So it also means this one. Yeah, but probably we will use this form because it exactly means that A is similar to D. A and D, they are similar. Okay, and the last one, we should express A to the power of n, A to the power of -1 in terms of P and D. In terms P of D, in terms of P and PD, in terms of PD, in terms P. For example, here, A to the power of n is this one, in terms of P and D, and D is this one. And so you should know what's the matrix P. P is this one. Just put the eigenvector, and D is this one. Just put the eigenvalue. But they have the same order. It's the most important thing. You should have the same order. Okay, so now I erase E. Since now we could really compute this example. So we erase E. Okay, so first step, find its eigenvalue. So just consider determinant A subtract lambda, right? So it's for its diagonal entry, we should subtract lambda. So it's 1 subtract lambda, and all another entry we just keep it. So it's this one. And its determinant is 1 subtract lambda times 1 subtract lambda, subtract 2 times 2, 4. So it's just, so it becomes 1 times 1 subtract lambda plus lambda squared subtract 4. This one. And then it's subtract 2 lambda. So it's lambda squared subtract 2 lambda plus 1 subtract 4. So it's subtract 3. But we should find its root. They be 0, find its root. So find its root. And here it means lambda 1, 3. But it's subtract, so it's subtract positive. It's negative 3 lambda plus lambda. So indeed it's negative 2 lambda here. Negative 2 lambda. So what do we have? We have it's equal to lambda plus 1, lambda subtract 3. Lambda plus 1, lambda subtract 3. So indeed, we know that lambda equals negative 1 and 3. Lambda equals negative 1 and 3. So it's the eigenvalue of A. Negative 1 and 3 is the eigenvalue of A. It's the eigenvalues of A. And if we denote by lambda 1, lambda 2. Okay, so it's the first step. Second step, find the eigenspace. So for the first step and the second step is just the result in section 6.1. So that's actually it's classical example. The example I will ask in chapter 6. Chapter 6.1 and 6.3. It's the classical example I will ask. Find the eigenvalue, find the eigenspace, find the matrix P and the diagonal matrix D such that A is equal to PDP inverse, and express A to the power of n or A to the power of inverse. Just A is inverse in terms of PD. Okay, second step, find its eigenspace. So we have two eigenvalues. So first one is -1. So if we denote by lambda 1, so its eigenspace, so we can say A subject lambda 1I. So it's A is 1, so for diagonal entry we should subtract -1. Right? So but A subject lambda 1I, what's this? It's exactly A subject -1, so it's A plus 1I. A plus I. A plus I, so for diagonal entry we should plus 1. Plus 1 is this one. So it's exactly 2, 2, 2, 2, this one. And what is this solution set? We want to find its eigenspace. So we should know 2, 2, 2, 2, 0, 0. And it's E to C, -1. And we cancel it. It's exactly just this one. And x1, x2. So it's satisfied 2s1 plus 2s2 equals 0. So it's equal to s2 equals -s1. S2 equals -s1. So what can we say? It's null space. So null space of A subject lambda A plus I is equal to S1, S2 is -s1. S1 could be any real number. So it's the spanning set of 1, -1. Spanning set of 1, -1. Yeah. So it's the eigenspace of A corresponding to eigenvalue -1. Corresponding to eigenvalue -1. And we still have another eigenvalue, 3. And we use the same way to figure out its eigenspace. So it's A subtract 3I. So for diagonal entry, we should subtract 3. So it's 1 subtract 3, 1 subtract 3. But off diagonal entry, we should keep them. So it's -2, 2, 2, -2. This one. This one. And again, find its eigenspace means that find 2, 2, 2, -2 is solution set. A0 is solution set. It's a solution set. And again, reduce it. So then we could cancel one row. Then now it's S1, S2. So it means that -2x1 plus 2s2 equals 0. And then move it to right hand side, you will get 2s2 equals 2s1. But we should divide by 2 in both sides as this one. Actually, we divide by 2 in both sides. So you could get S2 equals S1. S2 equals S1. So what can we say? Null space of A subtract 3I is equal to the solution set. Its solution set is S1, S2 equals S1. S1 could be any real number. And its spanning set of, you could choose one vector. So it's a spanning set of 1, 1. It's a spanning set of 1, 1. Yeah. So once we figure out the eigenspace, we almost could figure out the invertible matrix P and the diagonal matrix D. Okay? Yeah, so let's see what's the third step. What's the third step? Erase this part. What's the third step? The third step, let P be. Remember that we have two matrices here for the eigenvalue lambda 1. For the eigenvalue lambda 1, we have a vector, eigenvector this one, E1. You could choose one. So of course you could choose 1, -1, or you could choose 2, -2. Here, S1 could be any real number. So of course you could choose 2, -2. That's fine. Okay. So you could choose here. We could choose this one. So here B1 is this one. So here we could choose let B1 be 1, -1. And here we let be V2. V2 be the vector 1, 1. The vector 1, 1. So the matrix P is V1 put in the first column, so it's 1, -1. V2 1, 1 put in the second column. Let A be this matrix. D, what's the matrix D? D. So for this vector V1, eigenvector is corresponding eigenvalue is -1. And the V2 is corresponding vector eigenvalue is 3. So it's important to put it down in order. So here is our V1, our V2, then here you should put a lambda 1, lambda 2. So lambda 1 is -1, lambda 2 is 3. It's important order. It's important order. This one. Then you could write down the solution direct. AP equals PD. AP equals PD. This one. Then, and what can we say? Of course, A equals P, -1,0,0,3 P mers. And then, of course, for the matrix P, you could figure out its inverse. If you figure out its inverse, if you count it, you will see it's equal to 1/2, -1/2. Yeah, you could figure out the inverse of P. So for our matrix P is this one. For our diagonal matrix D is this one. Then we have this one. And here I could explain again here. As we say, why do we have this equation? Since we know that A V1 1 is equal to, the reason is that AV1 equals -1 times 1 -1. AV2 equals 1 equals 3 times 1 -1. 1 3 times 1 So in this case we know that AP equals A P in this matrix, V1 in first column, V2 in second column, it's our V1, it's our V2. So it's our AV1, AV2. This one. But AV1, okay, AV1 is exactly A1 -1, A11. But it's exactly -1 times 1 3 times 1 Here is -1. But it's important process. We could write in this way. It's 1 -1. Yeah, erase this part. Meaning for this matrix, we could write it 1 -1 1 and put the diagonal matrix. Consider the diagonal matrix. This one. And then it's our P. And then it's our diagonal matrix D. This one. So indeed, AP equals PD. AP equals PD here. But for this step, you could skip it. Okay, but you should know it's our P, it's our D. And if you change the order, you should change the order. Okay. And the final step. Find the A2, its inverse, and its power. Express it in terms of P and D. So A squared is equal to P -1003 P mers times P -1003 P mers. So its square becomes P -1 is square, 003 is square P mers. So it's P 1009 P mers. This one. Okay. Of course, for this one we could see this one is fine because it will be better to see the general form. A to the power n, it should be P times -1 to the power n, 3 to the power n. Let me see. Yeah, -1 3 times P mers. And how about its inverse? A is inverse. It's P 1003 P mers. It's inverse. So it's equal to this 10 P mers is inverse times P 1003 is inverse. So it's this 10 becomes P and this inverse becomes 1003 is inverse times P mers. This one. And then finally, for the diagonal matrix, its inverse is exactly, for its diagonal matrix, we consider its reciprocal. So just consider its reciprocal. 1 is reciprocal is 1. 3 is reciprocal is 3. The number 3 is reciprocal is 1/3 P dimers, and it's our solution. It's our solution. Okay, it's our solution. Yeah, so I give you the homework in this section. One ABC, two ABC, three ABC. Yeah, section 6.3. Okay, so it's the material in section 6.3. Section 6.3. And our final section is, we will introduce the section 6.2. It's an application. You could see it's an application. It's related to differential equation. Okay, let's go.